Hello everyone, and welcome to this latest webinar from IHS Markit titled Optical Transport for the 5G Era. Today our panel will discuss next generation packet and optical fronthaul, midhaul, and backhaul technologies for addressing 5G service, capacity, and latency requirements on the horizon. Our webinar is co-presented by IHS Markit and our partners Ciena, Fujitsu Network Communications, and Infinera. My name is Alan Tatara, Senior Event Manager for the IHS Markit Technology Group webinar team, and I want to thank everyone for joining us. So before we get started, I do want to highlight just some of the features that are available for you on the webinar and how you can make the most of your experience with us today. The console that you're looking at, it is completely customizable. So this means you can open, close, move, or even resize any of the windows that you have open on your screen and arrange the console as you wish. Now at the bottom of your console, you're going to see a number of application widgets. Make sure you check these out during the webinar. I do want to call out the resource list widget because this is where you're going to find additional material about our topic, including the downloadable slide deck from today's session, as well as other valuable information, including a special report authored by our own analyst, Heidi Adams. And all these materials can be accessed and downloaded right from your console. And we do want to make this an interactive session, so we've included a Twitter widget. You'll see that at the bottom of your screen, and this means you will be able to tweet directly from the console. Today, we are going to be using the hashtag 5GTransport. We will also have a live Q&A session directly after the presentation, so please submit your questions or comments at any time throughout the webinar by using the Q&A box that is on the left side of your screen. And if you do encounter any technical issues, just click on that question mark widget and you'll get the answers that you need. So now let me introduce our panel. First leading our discussion is Heidi Adams. Heidi is Senior Research Director in the IP and Optical Networks segment at IHS Markit. Joining Heidi is Denis Flouet. Denis is Senior Director of Portfolio Strategy at Ciena. We are also joined by Joe Masarino. Joe is a Principal Solutions Architect in the Optical Networking Group at Fujitsu Network Communications. And rounding out our panel, we have Dan Parsons. Dan is Senior Product Marketing Manager at Infinera. So welcome to our panel. It's great to have you with us today. So let's get started with our presentation. So Heidi, I will turn it over to you.
Thank you, Ellen. Warm welcome to everyone joining us for our webinar today. Over the next hour, we're going to be exploring some of the challenges and opportunities ahead as mobile network operators and those who sell connectivity services to the mobile network operators seek to transform their transport network infrastructure to be ready for 5G. From an agenda point of view today, we'll start off with a little bit of an introduction on the promise of 5G, 5G services, and when we expect to see 5G hit the market in earnest. We'll then have a look at the challenges that 5G presents to the transport infrastructure and have a look at some of the emerging technologies and solutions that are being considered to address these challenges. We'll then have a look at some real-world deployment applications and use cases and have a short overview of these solutions that our webinar sponsors bring to market in this area. So with that, let's get started. First off, a little bit of context and market trends on 5G. So the promise of 5G. What is the promise? Where are we heading? The diagram you see here on the slide is actually something I borrowed from a 5G America's paper on 5G services and use cases. I think it provides a really nice summary of the potential for 5G. It's a pretty busy diagram, but have a look at the broad scope of services. And we'll also have a look at the resulting complexity that as a result is going to need to be considered as you design 5G-ready transport networks. So if you look here across the top, range of 5G services covering human to human, covering human to machine and machine to machine interactions, along with some of the key service characteristics that you see up on the vertical axis, looking at the requirement for faster speed connectivity, as you'd have in enhanced mobile broadband, the ability to connect a massive number of devices, as you would see in IoT and machine-type communications applications, and also we're going to see with 5G this need to support the delivery of ultra-reliable, low-latency communication services. Example of that could be autonomous vehicles. So When you look at what 5G as a whole, what that's going to enable, to me it's really a platform that's going to set the stage for innovation in consumer services, but it's also going to encourage transformation across a wide range of vertical industries as well. So much in the way the internet set the stage for a new economy of web-based commerce and social interactions, I believe 5G also has this potential to open up a new economy and create new markets. So you could argue there's been a ton of discussion in the industry with respect to business models and how that's going to work for the network operators who are investing in this infrastructure, but there are some 5G-enabled applications that are going to kick off this investment cycle. We saw this morning Verizon's announcement of 5G fixed wireless services being available in 4 cities next month. So 5G is here. 5G is definitely beginning to ramp up. So let's have a look at the evolution of mobile services and how this evolution has impacted transport network infrastructure. So 1G, very basic, analog, won't waste time there. 2G was interesting because it brought in digital voice, a little bit of SMS, but really low speed, 64 kilobits, and effectively leveraged TDM as TDM is the underlying transport network. If you looked at 3G, that brought in the first of data, support for email. And of note here was that voice continued to be carried over PDH infrastructure, over TDM, and we saw the development of a new transport network often based on ETM technology, which was capable of doing both TDM voice and IP data traffic. 4G was a key transition because here data became the predominant payload, much higher speeds were enabled, full internet access and video services became possible, and at this stage the transport network moved to all IP. We saw a lot of packet, Ethernet, even OTM-based transport, and voice itself became a service over this network, leveraging IMS infrastructure for VoLTE as an example. So finally, 5G, support for a wide range of services. We're going to see a multifaceted evolution of the network infrastructure to add more capacity. We're going to see key network functions in the mobile layer becoming virtualized. We're going to see delay variation, low latency, security becoming critical for a lot of these emerging applications. So the move to 5G, it's getting underway. When are we going to see it? It is going to be an introduction that will happen in stages, much as what we saw in 4G. So LTE went from LTE to LTE Advanced, LTE Pro. The first of the 5G standards, 3GPP's non-standalone new radio, Release 15 specification, was frozen in December 2017. And the follow-on standalone radio specification was locked down in June 2018, so just this past spring. So the industry now has those initial standards and building blocks for the first of the 5G applications, and of course we're going to see more of that promise made available as you move into Release 16 from the 3GPP. So with early standards now available, IHS Markit anticipates initial 5G radio deployments will start in 2018. Of course, we're going to see that here in North America. We're going to see deployments ramp up. By 2020 timeframe, we expect China to hop on board and begin with their deployments. And by 2022, we anticipate that the total market for 5G radios and mobile core solutions will be over $18 billion. So this is going to be a significant market. But 5G deployments are not just about the radios. You also need a transport infrastructure in place to be able to make this happen. So we come to the objectives for our webinar today. There's a lot of questions around mobile transport for 5G. So, what is the impact of these new services, new radio technologies on the underlying transport network? We've heard a lot about fronthaul, midhaul, backhaul. What are these? What are the architectures? What are the options? And of course, we want to know what is going to be the role for the optical transport. Where will OTN, WDM, packet, and even IP/MPLS fit in as we move forward building 5G ready networks. So with that, I'd like to hand this over to our partners in our webinar to start describing the challenges ahead. And I'll start with Denis Flouet of Sienna. Denis?
Thanks, Heidi. So as Heidi said, 5G is exciting, brings different extreme capacity, reliability, connectivity, name it. But comes a lot of challenges with it in terms of transport layer to solve. If you break it down by where we are today with LTE and what 5G will bring in terms of journey, I like to split it in three different dimensions. The first one is what I call the mobile broadband services. That is basically what we as consumers are consuming today. This is moving us into more an enhanced mobile broadband service, but more so the ultra-reliable low-latency services and also the machine-type communication. And this means that the network now needs to be aware of different class of services, different latency, resiliency, scale, and more so the SLA, right? If you look at it from, that's on the service front. Now, if you look at it from an infrastructure perspective, we're moving from a world of monolithic nodal functions with all the functions, if you look at the radio and eNode B, were all co-packaged, into a world where functions are disaggregated. Control and user plane are getting split, or getting sliced. And this, again, creates a challenge on the transport side when you look at what does it mean in terms of performance when you start looking at fronthaul, the low-layer split, or the high-layer split, which is what people refers to the midhaul, and also the backhaul, the latency, and the slicing as well. Finally, there's also, with disaggregation comes virtualization as well, which IDs referred to as the cloud architecture. So we're moving from a highly centralized architecture from eNode B going back to the switching center to a way more distributed architecture where you're going to have different traffic patterns. Where will the content be located, creating NA to NA? End-to-end performance, not only on the radio side, but on the transport side, and also driving the slicing from an end-to-end perspective. All those things brings different considerations when you look at it from a transport perspective. Now, if you map this into simple deployment models, on the left side, you would recognize today's world. You have your consumer device, you have your radio equipment located at the cell site, all backhaul over different aggregation points, going back to a centralized location where the EPC or the gateways are located. It's highly an aggregated centric network where economics are driven by the level of aggregation you're doing in the network. If you look at what is getting introduced as a first 5G service, which is the eMBB, you would still recognize a similar architecture here where basically you still have a centralized EPC and where the traffic is getting largely backhaul back to the centralized location. So that's why most of the customers today will be deploying their current fixed wireless access or the new eMBB services largely over the current backhaul service. But when you move into the future of the deployment with ultra-reliable low-latency services, and you start mapping the distributed architecture with the edge compute and the disaggregation of the radio between RU, DU, and CU, you start to be facing quite a different challenge here. So the architecture changed drastically in terms of how the network will be built, the requirements that you have to deal in terms of latency, not only on data plane, but on control plane, and how the backhaul network needs now to take care of the new class of services that 5G will bring, the new latency that will be extended in the backhaul, wherever the content is located. So we're going to be moving from a highly aggregated centric backhaul network to something that I like to call more a performance-centric network with the right economics in place. Now I'm going to turn this over to Joe.
Thank you, Denis. Migrating from a 4G network architecture to 5G has several topology similarities for reuse. However, 5G transport will also add multi-point to multi-point connectivity. The 5G backhaul will use carrier Ethernet facilities similar to 4G or a higher performance layer 3 network to enable future network slicing and virtualization case uses. The new generation fronthaul interface has two modes of operation. One is general mobility, and the other is for ultra-reliable, low-latency connectivity. Mobility requires 100 microsecond latency maximum, similar to what we currently have with 4G architecture. And the ultra-reliable, low-latency connectivity model is at 50 microseconds. Therefore, for general mobility use case, fronthaul transport facilities from the 4G network can be blended with 5G services. The ultra-reliable, low-latency connectivity use case will require a transport facility at half the distance or less than that of the 4G, resulting in a maximum of 10 kilometers between cell site and distribution units. Timing and frequency accuracy is more stringent for 5G fronthaul using PTP and SYNC-E. The midhaul segment is new to 5G, and based on mobile network operators' architectural functionality, this segment can become an additional optical transport path and or be integrated into all parts of the existing 4G fronthaul network. A variation from 1 to 3 millisecond latency budget exists here, and the variation is based on radio vendors' functional split of 2, 3, 4, and 5. The midhaul latency budget is 1 millisecond, and using functional splits 2 and 3 yields up to a 3 millisecond latency budget. Massive MIMO technology used with 5G radios will drive the network to even higher capacities. Backhaul latency maximums are unchanged from 4G to 5G, but backhaul transport capacities will grow from 10 gigabit rates to 100 gigabit rates. So let me hand off to Dan.
Thank you, Joe. With LTE services, content could traverse the network. However, in 5G, even if you have the lowest latency transport, say running at the speed of light, it really forces you putting content closer to the end user to achieve those low latency services. And thus, the multi-access edge computing puts the cloud or the service edge to within about half a millisecond, and corresponds to about 100 kilometers away for those ultra-low latency services. Now, to achieve the 5G radio performance, higher radio spectrum is used, but it's at the expense of poor propagation. And thus, more 5G radios are needed to be deployed, and they have to work within the existing 4G cell infrastructure. Now, to achieve this, a 5G transport is more than just the capacity and latency. It's about connecting the radios to each other and providing that precision timing and synchronization so that the 4G and 5G radios can be coordinated and work together. Here we see how timing and sync performance was key in LTE advanced network. Technologies such as enhanced intercell interference coordination, or ICIC, and coordinated multi-point, or COMP, can improve the radio's performance significantly, up to 40% more throughput as a result of precision timing in among the radios. And this is absolutely critical when you think about the investment being put into the radio system. And the spectrum is the greatest asset for a wireless operator. When you think about the 2015 FCC spectrum auction, AT&T and Verizon spent between $16 billion and $20 billion each for their spectrum. So they want to maximize the amount of capacity of that investment. Such LTE advanced aspects as carrier aggregation and multiple input, multiple output, or MIMO, are used in 5G, but it requires even tighter timing and synchronization. Almost a factor of 10 for carrier aggregation, and a factor of 20 for the beamforming massive MIMO of 65 nanoseconds. But this really highlights a salient point that can get lost in all the activity around the 5G radio, is that transport needs to be in place first before you really can achieve the 5G radio experience. So back to you, Heidi.
All right, so thank you, folks. So with that, we're going to move into a new section, and we're going to have a look at some of the fundamental technologies that are going to be key in the evolution of mobile networks. So let's start off with Denis.
Thanks, Heidi. So when you look at the challenges that Joe and Dan just discussed in terms of latency and timing, obviously that's a criteria that we need to consider when you look at selecting technologies. We know what this is all about when you look at it from a C-RAN perspective with the latency, and largely customers have deployed this today over dark fiber or passive or active WDM systems. But when you look at and if you look at where the market is going with basically the disaggregation of all this and the different deployment models with the 5G, there's a new set of requirements, again, as discussed by Joe and Dan, in terms of what it means to overall the performance you need to achieve with the right economics in place. That's one set of criteria you need to consider. The second one is also the slicing. So what is slicing? So slicing is the ability to basically, it's a new paradigm with 5G. It's the ability to basically allocate resources in your network where you need it. Resources that could be against a mobile broadband service, resources that could be assigned to a low latency service, or resources that could be assigned to an MVNO type of business model where you basically slice in your network to allocate to an MVNO. There's a definition called hard slicing, which is there's no level of sharing, there's no level of stealing from one service to the other. It's really hard, boundary-driven type of slice that you can refer to as a TDM structure. And there's a soft slicing, which is way more on the sharing side of it, which is pretty close to what the packet behavior has been on the network side. So those are the two criteria when you look at it from on top of the scale and the other transport requirements that we usually deal with that you need to pay attention to when you start looking at what is the right technologies to deploy in the network. We have created a small table here that basically highlight the different discussions taking place in the overall industry when you look at transport. We like to summarize it in two different main categories. One is what we call, it's in the blue side of it, on the top of the chart, it's called data plane transparent transport. And the other one at the bottom is called data plane engineered transport, or if you want, traffic engineered type of network. So if you start with the data plane transparent transport, today OTN has been well known as quite an effective way to transport transparently services between A and B. What is required here with the mobile OTN and the work that is being addressed by ITU is really to optimize the OTN structure from an overhead perspective, from a container perspective, to really be optimized for the mobile side of the house. And that's what is called the mobile OTN. So all this is done to address really low latency capabilities over an OTN structure and maximize the benefits of this OTN. With OTN, you get hard slicing. By definition, that's what OTN is all about. You get transparency, you get latency, and you get deterministic by the design of an OTN network. And this is a work that just started in the ITU side, and it's going to become standard over time, over the next few years. If you look at the core of the network, there's still the OTN as has been deployed by many of you, many large carriers in the world, that still has a valid play into the mobile network, providing hard slicing, transparency as well, and extending the efficiency of the transport network, and really being deterministic nature for the underlay of the MPLS or the segment routing or the layer 3 VPN type of construct. So really a data plane that is transparent, that enables to leverage the multiplexing capabilities that you get with those technologies, the resiliency, and the deterministic nature of those technologies. On the bottom part of the chart, you have what is emerging as the traffic engineered type of transport. On the left side, you have something called TSN, which stands for Time Sensitive Network, and ROE, which stands for Radio over Ethernet Network. And those technologies are meant to turn the fronthaul network into a more ubiquitous Ethernet type of transport system that would deliver on the value of deterministic nature. So turning Ethernet from a best effort to something that you can rely on, you know that the bits will be delivered. And with those technologies, you can really address the hard and the soft slicing. You can address the latency and the deterministic nature of it, while still having access to that stat maxing gain that drives the economics of such a packet there. On the right side, the other technologies that is getting discussed in the industry, although not yet approved as an ITU project, is what is called the SPN, which is a sliced packet network. It's a concept of turning FlexE into a network type of environment. So today, Flexi is largely a uni type of management system, but this is basically turning it into a networking environment. And by doing so, you can get some values about the hard and the soft, IP multicasting, deterministic as an underlay for the MPLS-SR, and you still have the stack mixing gain. So really, different technologies are starting to emerge, the mobile OTN, the TSN, the SPN, leveraging current technologies like OTN as well, and the IPMPLS and SR coming up soon as well in some of the customers. All this is basically to address what we discussed before, the latency and also the slicing requirements that we see emerging as strong requirements for the future of transport network. At this point, I'm going to turn this over to Joe.
Thank you, Denis. As Dan, Denis, and I have shown, there are many new architecture and interface types in 5G transport. And here I will briefly review where these new interfaces are coming from and how these interfaces are being driven to an open standard. There are several standard and de facto standard technical bodies defining protocols and interfaces for 5G transport. Some of these bodies are listed here and are working with the service providers and vendors to establish an open xHaul ecosystem. The xHaul ecosystem consists of backhaul, midhaul, and fronthaul transport segments, as we viewed on my previous slide. And in an open ecosystem, all the multi-vendor network elements will interoperate. The CPRI cooperation is where the fronthaul protocols were established. OPSI and CPRI for 4G, eCPRI at 25 gigabit per second for 5G. Derived from a consortium of 4 radio vendors, there are still proprietary aspects in the payload preventing multi-vendor interop. IEEE has established a time-sensitive network structure, or TSN, as published in 802.1 CM, and a method for blending legacy CPRI, eCPRI, and radio over Ethernet encapsulations onto a TSN transport path through IEEE 1914.3. TIP is driving the open virtual RAN by bringing together CRAN and XRAN. XRAN, the CPRI cooperation, and IEEE 1914 are being combined here in this body to an open protocol. This will enable interop between vendors, thereby lowering risk and cost to MNOs. Let's compare these new 5G protocols and rates to the current 4G xHaul architecture. While the 5G RAN operation offers 10x plus greater broadband rates over 4G technology, the transport can become cost prohibitive for MNOs. In the 4G CPRI model, in the fronthaul and carrier Ethernet, there is backhaul. CPRI frames are fixed and do not scale economically for the greater 5G capacities. In the 5G RAN model, you have eCPRI and radio over Ethernet operating in the fronthaul. eCPRI and radio over Ethernet frames are variable, unlike the CPRI frames, which are fixed. Therefore, 5G fronthaul does not transport idle streams, thereby reducing the transport rate. To further reduce transport rates, the 3GPP developed a series of options to split the BBU into 2 processors, forming the central unit and distribution unit. The 3GPP has several functional split options that have been debated over the past several years. Currently, option 2 is the popular functional split for this section, which is referred to as the midhaul, or sometimes referred to as fronthaul 2. Some BBU functionality was also transferred to the radio head, now referred to as the radio unit. These functional processing splits reduce the transport rates, leading to lower transport costs. Let's see how these existing 4G and new 5G technologies are applied to the platforms. The 5G fronthaul, which is the DU to RU section, will have multiple 25 gigabit per second channels of eCPRI or radio over Ethernet based on the number of 5G bands and sectors per cell site. Brownfield sites will also have 4G CPRI traffic to be transported as well. Unless the mobile network operator has an abundance of dedicated dark fiber, these channels will have to be multiplexed for economical transport to the central DU pool. TSN and or WDM can be used here. A TSN transport MUX is a layer 2 platform based on IEEE 802.1cm, offering Ethernet SLAs with timing and synchronization to maintain fronthaul operation within the 100 microsecond latency maximum. Platforms capable of IEEE 1914.3 will also provide CPRI agnostic and aware modes to blend 5G eCPRI radio over Ethernet traffic with legacy 4G CPRI traffic on the same fiber path. WDM active or passive elements similar to what was used in the 4G architecture using 25 gigabit per second optics are another low latency option. Like TSN, WDM can also blend 4G and 5G traffic on the same fiber path. Advanced platforms include automatic protection switching and OEM for remote visibility. For midhaul, the central DU site will consist of multiple DUs in a pool, providing resources to multiple macro sites. 100 gig packet optical layer 2 or layer 3 Ethernet and OTN-based aggregators are used to multiplex 10 gigabit Ethernet over 100 gig streams between DUs and CUs. Backhaul will use carrier Ethernet, or to facilitate future network slicing, programmable layer 3 routers would be used with 100 gigabit Ethernet scaling. Let me hand it over to Dan.
Thank you, Joe. So here we see a high-level view of a 5G RAN with DRAN and CRAN implementations with the protocols mentioned by Joe and Denis. The fronthaul, midhaul, and backhaul could be point-to-point protected point-to-points or rings, as mentioned previously, to provide those ultra-reliable low-latency services. But let's take a look at the capacity first through this network. Now, from the radio units, the RU, to the distribution unit, the DU, fronthaul eCPRI could easily exceed 25 gigabits. Now, why do we say that? Well, each cell could have 3 sectors supporting multiple radio bands. And depending if and how massive MIMO is implemented, that will affect the capacity. For example, if massive MIMO is done with a DSP at an active antenna, then you only really need one radio link. All the processing is done by the DSP. But if it's processed in the radio digital baseband, you'll need multiple radio links. And there you can see the capacity exceed 100 gigabits. Now, depending on the number of cells and latency requirements, the DU to CU, or the midhaul, could be more than 100 gigabits. Now, at the CU, where the multi-access edge computing platform is located, you can have multiple 100 gigabits, and then you can see that rippling up into a terabit backhaul. So here we can see the impact of capacity throughout the network. However, in 5G, timing is everything. With 3G, it was enough to assure the handoff. In LTE advanced, timing was definitely more of a factor for radio coordination and interference management. Now, one way we could implement a very precise time network is to provide a GNSS or a global navigation satellite system, a GPS, at every node, so that you can have the precise time of day without any differences. But this isn't practical. You can see that it can be very expensive, say, putting one of these receivers at every cell. Also, too, implementing indoor would be an issue. You can get RF shadows. You imagine building a radio network and then somebody erects a building and blocks your GPS, so you have an RF shadow. There could be jamming. You jam the signal, and of course, these satellites signals could be subjects of political, and therefore you could have problems with that. So the network synchronization is going to be implemented, and there's standard mechanisms to do that already in place. For instance, the IEEE 1588 Precision Time Protocol, or PTP, as mentioned earlier by Joe. Sometimes these are embedded in the network elements themselves, and a boundary clock, the BC, is essential because it compensates for delays in the network. It refreshes the timing packets and helps maintain accuracy traceable to that grand master, that primary reference clock for time and phase. Now, the total time and sync difference between the grand master and the cell across the entire network has to be less than the 5G time division duplex frame of about 1.5 milliseconds. Let's take a look at latency now. We see the difference here, as I mentioned previously, for the ultra-reliable low latency and the one for mobile broadband, 0.5 milliseconds to 4 milliseconds. But I'd like to point out here about latency, about path asymmetry affecting the timing. How could that happen? Well, in eCPRI, a path could be switched, or the distance is not taken into account. For instance, if you just consider the speed of light in a vacuum at 3.3 microseconds per kilometer, we see that a difference about half a kilometer in the effective latency for comp could cause an effect here and ruin the timing. And in massive MIMO, 65 nanoseconds, that's only 20 meters. So as a result, some fronthaul and transport technologies employ delay compensation here to overcome this effect. So I'd like to turn it back to Heidi.
All right, so having gotten a view of some of those key technologies, let's have a look at what we're starting to see in the industry in terms of deployment examples. So we've got a few good ones to share, and let's start off again with Denis.
Thanks, Heidi. So for the last 30 minutes, we've been talking a lot about latency and capacity and timing, and different technologies that basically are meant to address those challenges. Think of TSN, or think about mobile OTN, or any other technologies. So what you have here is basically it's a subset of what we believe will be the deployment models going forward in terms of network. First of all, we strongly believe openness is the way to go, and that's why if you look at this chart, you'll recognize some logos here in terms of having a live network that has been built to really represent an open ecosystem, leveraging the power of everybody to turn this network into reality. So disaggregation and virtualization doesn't mean that it's a closed market. It's basically an open system. This being said, if you look at how deployments model will happen, we believe if you look at the left side, there's two main deployment models we're going to be experiencing. On the top left side of the chart, it's called CRAN and DRAN co-deployed. Many of those sites today have LTE networks and will receive 5GNR networks as well. And in some cases, some of them will be CPRI-based, eCPRI-based, some of them will be DRAN-based. And it's important that you build a network that where you can share those transport level and drive the right economics of behind it. And that's basically what we are demonstrating here on the top left side, as I said, where the TSN technologies truly shine, where you get basically the stat marking gain and really and you deliver on the tight characteristics of the CPRI and the CPRI signal while still enabling the transport of the backhaul system. Different deployment scenarios will drive different selection of technologies, and here we believe that the TSN brings a lot of value in the access by really enabling this mixed traffic scenario. On the bottom part, it's largely a CRAN, a pure play CRAN type of deployment, eCPRI or CPRI, where those could be co-deployed as well. And as a result, today, as you all know, dark fiber or passive WDM or active WDM has been used. As I discussed before, mobile OTN is really a way to really enable this type of construct, being native CPRI over mobile OTN or leveraging the IEEE 1914 radio over Ethernet as an encapsulation for CPRI over Ethernet. And by having this basically driving the right performance of the network over a highly multiplex network, leveraging OTN capabilities with the low latency characteristics back to the BBU. So those are the two deployment scenarios we see on top of what is being deployed today, as I said, with dark fiber and passive WDM systems as well. In the short term, when you look at the backhaul being this network being largely an NSA mode, a non-standard standalone mode still managed by EPC. This means that basically you can leverage the current backhaul network you have, augment with capacity and new connectivities as you need it for the 5G. But this is largely can enable in the short term the current IP/MPLS core that you have to really deliver this backhaul network. So those are basically the building blocks that as we engage the market and we engage customers are the key building blocks that keep coming back in terms of the likely deployment models that we see happening in the network. Joe?
Thank you, Denis. In a split architecture, the DU connects to many macro site RUs over multiple front haul fiber paths. This is a similar architecture to the 4G central RAN or CRAN, where there is a central point, a pool of DUs in this case, spanning out to multiple macro sites for interconnect with the 5G radios, otherwise known as RUs or transmission reception points. This efficient technique is referred to as RAN pooling, and along with cell site aggregation, offers mobile network operators the ability to engineer the RAN capacity based on clusters of cell sites coming into the central point DUs instead of engineering the network based on individual cell site demands. For latency-sensitive operation, the distributed DU use case is where DUs are co-located with the RUs at the cell site. The distribution DU, or the distributed DU use case, offers a latency-sensitive architecture by eliminating the front-haul transport path. The front haul becomes a local connection between the top and bottom of the tower via a fiber cable. This is a low-latency configuration, also lowering costs by eliminating the front-haul transport section. The trade-off here is loss of multi-site pooling and cell site aggregation with macro cell sites. The mid-haul capacity is reduced to 10 gigabits per second. Finally, there is the integrated DU, which is the distribution unit integrated into the radio unit at the cell site. This architecture offers similar benefits as the distributed DU with an additional advantage of lower CapEx and OpEx through the integration of DU and RU. Let me hand it over to Dan.
Thank you, Joe. So Heidi mentioned before when we started that it's about transformation. But here we see an example of something we did before of 3G to LTE transformation. And I look at it as an example for a transformation of 5G. This is a real example of a RAN transformation for a new generation radio. In a typical 3G network, it upgraded to an LTE advanced with a new packet optical transport system of 10 times the capacity. However, it was the network's precision timing and sync and low latency to support comp that really enabled that radio performance, over 30% better radio performance. So again, emphasizing the point that timing and sync is essential. It's going to be very key in 5G. Moving on to another example here. We see that with the increase in the number of small cells, the demand for 5G connectivity will increase, and this really opens an opportunity for enterprises such as smart cities, utilities, and MSOs who have a very expansive deep fiber infrastructure that can leverage it, that can be leveraged for wholesale RAN transport connectivity. But it's not only supporting the physical fiber connectivity, but also supporting the independent time and sync domains for each mobile network operator. This could imply building a separate network for each operator if the platform only supports one timing domain. And we have an example here of an operator. This is a published case study here of an operator that does provide RAN transport wholesale provider managed mobile fronthaul and mobile backhaul services. And this is Hutchison in Hong Kong, where very dense urban application makes it ideal setting to connect the cells. So back to you, Heidi.
All right, so to wrap this up, I'd like to give each one of our sponsors an opportunity to share a little bit with respect to some of the solutions they're developing in the 5G mobile transport space. So actually, I'll start with Dan this time. Dan?
Okay, thanks, Heidi. So the challenge that exists is deploying a RAN infrastructure and transport equipment that LTE Advanced could use right now, but it's not going to be obsolete for 5G. Now, if you had to make a wish list for a transport platform to support 5G transformation, it could look something like this. A platform that not only supports the capacity and low latency 5G interfaces, but also has the flexibility to support multiple network operators over the same network, provide the latency compensation and programmable fronthaul implementations, as we discussed in this webinar. It could also support technologies like WDM-PON to reduce the fiber count to the radio unit sites. Now, with that, I'd like to hand over to Denis.
Thanks, Dan. So when you look at the solution, and we've been talking about scale, performance, you look at different dynamic network, and we've been talking about slicing as well. You need different elements to really turn this network into what the mobile operators are looking for in terms of really an adaptive network. And that's basically where Ciena would be leveraging its packet networking innovation as well as our WaveLogic innovation, as this network requires way more scale and performance than what we have seen before. All this wrapped into our orchestration strategy as well. So the key building blocks here really to enable this type of a network to become reality and to really unleash the services that are required with 5G. Joe?
Thank you, Denis. Fujitsu has a complete end-to-end, open and disaggregated solution for 5G radio access network, or RAN. This solution is based on Fujitsu experience in 4G RAN transport using our smart xHaul system with over 2,000 4G fronthaul network elements and hundreds of thousands of backhaul network elements deployed. The solution includes optical and packet optical, smart xHaul platforms, 5G radio units, along with fixed wireless access radio units, virtual DUs, CU elements, standardized SDN management and control software, along with our turnkey services team that can design, integrate, deploy, and manage the entire network. Let me hand it over to Heidi.
All right, so just as a reminder, as we get close to our Q&A section, please feel free to answer or to enter your questions into the interface on your console, and we will have a little bit of time at the end to address a few of them. So to sum up what you would have heard today on this session, 5G we know is going to enable or has the potential to enable a wide scope of service innovation, and there is going to be direct impact on how we design and build underlying transport infrastructure in order to meet these new requirements. In addition to that, very, very clear that there's going to be very close coordination needed both between the radio network, the network elements, and to enable some of the functionality there. key close coordination between the radio and the transport layer is going to be critical as we move into 5G. And finally, as you would have heard from our presenters on the session today, there are new technologies, there are new protocols, there are some new approaches emerging that are now starting to become available on the market to help with this transition towards preparing 5G ready transport networks. So with that, let's move over into the Q&A section. There's a ton of questions that have come in today. We won't be able to get to all of them, but let's see how many of these we can work through. I'd just like to preface a little bit. There are a few questions that are a little bit more around some of the radio layer type characteristics, and we'll try and address those offline and keep focused on a little bit more the underlying transport piece in our discussion. And there were several questions on microwave, and I just want to say a quick word on microwave. Of course, there are use cases for microwave in front-haul applications, and as we know, microwave is a key enabling technology in backhaul and is very widely deployed in the market today. I'd like to put this aside and say we'll be addressing this in a future webinar topic, so keep your eyes open for that if you'd like to dig into that a little bit more, and I'd certainly be happy to point you to where you can find some more information on that. So with that, let me flip over and just kick off the Q&A section with a couple of questions with respect to front haul to start off. So we had a question here actually, hang on here. Just a couple of questions with respect to front haul. First one, as you look at 5G transport platforms and you look at front haul, what are the resiliency mechanisms that we're looking at? I'm wondering, Joe, if you could take that question.
Sure, I'll take that one, Heidi. Thank you. There's two types of resiliency that are available. For active WDM, ring protection using all optical switches for self-healing based on loss of light, or signal degradation using program threshold points is typically used. In fact, that's what we used in our 4G front-haul network deployments for resilient operation. For 5G TSN front-haul, you would use optical or electrical detection and switching to provide a self-healing ring. Optical would use all optical switches. Electrical could use OTN protection switching, G.8031 or G.8032, typically found on packet optical platforms.
Okay, great. A little bit different, looking at the different access technologies, and of course I just put microwave aside for the moment, but WDM-PON is a potential technology for front haul. So why would you not just use active or passive WDM? Dan, would you be able to tackle that one?
Yeah, sure. Well, I guess with WDM-PON, what makes it different from just a simple WDM is that not only are you getting a fiber gain, because there's going to be a lot more fibers deployed, it really facilitates mass deployment because you have auto-tuning technologies. You can just plug in SFPs and they can tune based on the filter ports. They kind of find each other's wavelengths. Whereas with, say, just WDM, there'd have to be a wavelength planning, matching the wavelengths to the ports, and that just doesn't make it easy for mass deployment. So that's why WDM-PON is attractive for that.
Okay. I had a foundational question that I'll just ask it for the benefit of the audience for those who may not be as familiar with it. But when you're looking at front haul distances, what are going to be typical reaches you might have between a radio head or antenna and a centralized baseband unit? Denis, do you have that data off the top of your head?
Yeah, so when you look at the CRAN and you look at it in the context of 4G, basically you are into the 150 microsecond type of round trip, which equates to roughly 15 to 20 kilometer type of range. ECPRI will be in the same model if you go with an enhanced mobile broadband type of deployment scenarios. But as soon as you start looking at ultra low latency services, it changed completely the landscape. And here you're going to see really requirements on the front haul going down to few tens of kilometers if it's not just a single-digit kilometer type of reach. So you have to really be careful to understand what are the services you want to deploy, what will be the deployment model, where will be the CU and the DU located, and as a result, what does it mean when you look at it from a distance perspective.
Okay, great. Thank you. All right, here's a question I'll open up to the full panel, so just jump in if you have an answer to this. As you look at different data rates across different 5G bands, so depending on what spectrum you're using, you could be driving the requirement for different data rates. How do you do planning for a network in this a transport network in this kind of environment? So do you need to over-dimension for sort of the largest consuming hunk of spectrum, or are there ways to adapt it? So let me put that out to the panel. Would anyone care to jump on that?
I can, this is Joe from Fujitsu. I could take a first crack at that, and I think my colleagues would also probably want to chime in. But typically, what you're seeing when it goes from radio to the digital format, it's going to be an eCPRI or radio over Ethernet. These are variable frames so that there will be a variation in terms of the actual bandwidth capacity that will be passing through the system. There are calculations that I know our radio group at Fujitsu uses to transform the radio spectrum into the actual capacity that will be required, also based on the number of antennas that are connected to that particular radio. So there's a number of calculations that can be made, but also when you do get to the eCPRI or radio over Ethernet point, it is a variable frame, so it can be essentially statistically multiplexed if it's a general mobility type of application.
Yeah, I agree,
right,
Joe. This is Dan in Finera. Yeah, it's the calculation. You have to plan on what radio bandwidth you use in that calculation Joe mentioned. There are documents out there that published documents to help plan that. It all has to do with the radio bandwidth, the number of antennas, how the MIMO is implemented. So it's not as straightforward. It's not just CPRI equals the number of is the IP data rate. It's the radio I and Q. So there's quite a bit of calculation that needs to be done in it. But it's as Joe mentioned, there's documents out there that help with that for sure.
All right, great. Thank you very much. All right, just time for maybe one or two more quick questions. I saw something pop up with respect to the timing and synchronization side of things, and it's a question with respect to implementation of GPS systems directly in the cells, and in particular in small cells. So is that going to be an option go forward, or are we going to start to see more of reliance on leveraging timing and synchronization capabilities in the transport network? Maybe Dan, I'd throw that one over to you.
Could you repeat the question again, Heidi? I was hoping
use of GPS, use of GPS in the radios and small cells, as opposed to relying on the transport network for passing timing and synchronization information.
Yes, If you use GPS everywhere, well, it could be expensive, and also too, you're relying on the line of sight with the satellite, and that's not always practical. So there are mechanisms that the network can deploy that once you say time the network and have a grand master, that grand master can be referred to all the way through the network, and such technologies like IEEE 1588 boundary clock assures that. So that's why.
Okay, great. I see we're at the top of the hour, so I'd like to thank the panelists and also hand over back to Alan to wrap us up for the session today. Alan?
Thank you, Heidi. And I want to thank everyone for participating on our webinar as well and for submitting all your questions and comments. As Heidi mentioned, we have received a very large number of questions, and our panel will follow up with you via email. I do want to thank Heidi for leading our discussion today, as well as our speakers, Denis, Joe, and Dan. Thank you for sharing your expertise with us on our webinar. So an archived version of this webinar will be made available shortly, so feel free to come back, view this session again, or even share it with your colleagues. Now you will see a short survey pop up at the conclusion of the webinar, so we'd love to get your feedback, so please take a few moments to fill that out. And lastly, make sure you continue to follow us on Twitter and LinkedIn for information on future IHS Markit Technology Group webinars. So again, thank you for joining us, and have a great rest of your day.